into memory. Don't try to optimize it by keeping it in a register, because that would sort of thwart what we're trying to do in our benchmark, where we're trying to see how fast we can touch memory. So we just have a little loop here, and you pass in how many elements you want to examine, and you pass in what the stride is, and then we treat this data that we're accessing like an array, some hunk of memory. We want to walk across and touch and just read it. We'll just take it and add it into the result, doing some silly little addition or something. Basically, just to do something as we walk across this chunk of memory. And then when we get through with the result, we'll stick it in the sink, which forces the compiler to not take this code and just throw it in the trash can and optimize it out of existence, right? So we made this result, then we stuffed the result into memory to force him to actually emit code to do that. So then we run the thing with a little run function that calls the test function. And so what we're going to pass in is the size, the number of elements we want to look at, and what the stride is. And then we tell it, the run function, what the speed of the processor is in terms of megahertz, and we convert that to express our results in terms of cycles. This convert the cycles, the megahertz, into how many megabytes per second we're actually getting in throughput. So we'll run the benchmark on the Core i7 with these caches, these size caches, 32K, the 256K, and the 8 meg. And I think this was like a 2600 model processor this was executed on, which is the processor that's on the computers in the Linux pool. And you'd get a picture out that looks like this. And so you see you're varying the stride. How far is the next memory reference from the current one? And that stride 1 is what we really want to make things go fast. And you see if we get over with the stride, that curve is going up, right? We're getting a lot of throughput, megabytes per second. As the stride gets worse, it's going down. We're going to vary is the working set size, the total amount of memory that we're going to try to access. And we're just going to run around repeatedly and do it over and over and over again and get some numbers out, right? And so the working set is a term we use, and we'll use later when we look at how virtual memory works, a process's working set. But roughly think of a collection of addresses that the process is going to want to access, right? How big is that collection of addresses that for some short burst of time this thing wants to access that collection of addresses. So we're going to vary with the size of that data that we were walking across in the array, what that working set size is, right? And you see the obvious things happening when you make the working set bigger and bigger and bigger, holding the stride constant, going in terms of the as you make it smaller, rather, you're going up and up and up in terms of the speed that you can do things. Because why? Because it's fitting in the cache, right? And as you make it bigger and bigger and bigger, right, it's going down and down and down because it isn't fitting in the cache. Well, the little teeny L1 cache, we'd have to make it real small for things to fit in the L1. So the L1 effect would be up here, the L2 effect, the L3 effect, and then the main memory would be these things down at the bottom. So we get these pictures, and we get some things that we call slopes of spatial locality. See these little slopes here? See that slope? And it's kind of hard to see, but you see it sloping off there, right? Well, that's the effect of the spatial locality of the references, right? What's affecting the spatial locality? Well, the stride certainly, as it gets bigger, is getting worse and worse spatial locality. So we'd expect to see this going up, this little slope to the left there, as we made the stride smaller, which is exactly what we're seeing. And then if you go to the next slide, we these ridges of temporal locality, right? So that ridge there, this is the effect of the L1 cache, right? If you made the working set real small, it fits in the L1 cache. You get some really nice high throughput as long as your stride doesn't get ridiculous, right? It doesn't matter if what you're trying to put in there fits in there, if you're jumping to some distant memory location that isn't in there, right? So as the stride gets bigger, it's having an effect on it, slowing it down. And as the working set gets to this worst point right here at the bottom, right, with your worst throughput. And then the things that are affecting the throughput are reducing the stride, making it go up these slopes, right? And making the working set smaller. You're going up and up and up toward the top. And this is saying, you know, things right up here fitting in the L1 cache. Well, it's too big to fit in the L1 cache. So you're sort of throttled by the speed that the L2 could supply things to you. And here it gets so big, you're at the L3 level, and here it won't even fit in the L3, and you're down in the main memory, right? So given those cache sizes, you're seeing that kind of behavior. And so that's, you know, pretty obvious stuff. So then when we write our programs, we'd like to be able to live up here where the L1 was really working good for us, right? But maybe the stuff that we're working on is so big that the L won't fit in the L1. Well, at least we could get this effect, right? So we want to learn to write programs that exploit this as much as possible. So how do we do that? Well, the first thing we look at is a classic problem that's been studied maybe more than any other problem on supercomputers trying to figure out how to do it fast. Just plain old matrix multiplication. There's tons of scientific calculations that you want to do. The math that you ultimately are doing in those calculations boils down to, well, I need to multiply some matrices, right? So we'd like to be able to figure out how to make that run fast on the computer. So this problem has been studied to death. We want to look at a sort of a first attempt to analyze it here today. And if you remember your algebra, of course, you take a matrix that's an I by K. You can multiply it times something that's K by J, and you get a matrix that's I by J, right? The inner ones have to line up. The number of columns in the first one has to be the number of rows in the second one, because you're going to create all those inner products by pairing them up, multiplying them, and adding, summing it up, right? So those dimensions have to align for it to make sense to multiply the matrices. So we'll have three parameters going here, right? I, K, and J to produce this IJ matrix. Make sense? So we'll use in the example here, we'll use a line size just for the heck of it of 32B, big enough to hold 4 64-bit words. So that'll be the just the parameters of this analysis, not necessarily the real computer, but this is our example. So we'll have a 32 byte line size in the cache, and that'll hold 4 64-bit words, right? So we'll assume that the dimensions of the array are just really big, so big that the array will not fit at all in our caches, right? The cache isn't big enough to hold multiple rows. We get this huge array, right? So that's the analysis we want to do. What if we had that situation? Well, if you just went over to your math book and you said, well, how do you multiply matrices? And you copied it right down out of the math book, you might come up with some code that look like this. I got 3 things I need to vary, the rows and the columns, right? And then within that, I times J products that I want to end up with. I want to compute I times J inner products. To get an inner product, what do? Well, you take the row and you walk down all the elements in the row and you multiply it by walking down the elements in that matching column, right? The I and the J, and you get the product element at the IJ position in the product matrix. That's your little inner product, right? Everybody remembers that from linear algebra. So That's what I would write down if I just thought, well, what did they teach me in the math classes? How do you multiply matrices? That looks like it, right? I got to compute up all these I times j results. And to get each of those results, I've got to compute that inner product and put it in a position in the result matrix, right? So far, so good. So we want to look at that and say, well, how does it actually work on the computer, given the assumptions that we had? So the array in C, of course, is stored in memory in row major order. So it looks kind of reasonable. I got my I, and then inside the I got the J. So that looks relatively reasonable. And so then stepping through the columns in one row in the inner loop, varying the rows, accessing the successive elements. Well, they had an assumption that B was big enough to exploit the spatial locality to some degree. They said, okay, suppose we could fit 4 64-bit words in this block, right? So they're saying, okay, great. You touch some location and you miss, and then you hit 3 times, right? So that's the kind of thing that they're trying to use for this loose analysis, right? So we step through the rows in a column. That doesn't look so hot, right? This one up here, stepping through the column in the row, was our nice stride 1 stuff, right? We're holding the row fixed and then incrementing I. We're just hopping over to the next 4-byte entry. So when we touched 1, we got 3 for free. So we're getting our, nice stride 1 stuff. That's working good. But what about here? Well, here we're holding the column fixed and walking down all the rows to walk down the column, right? Which is what we have to do, right? And this term over here is walking across the row as we go through the inner loop, but this term is walking down a column. And so that's a stride in access, right? We're jumping n times the size of the data elements away in memory to get to the next one that we want to touch, which is not very tight spatial locality. It's not very appealing to us. We know that's going to hurt us with the caches, right? So there's not much spatial locality going there. And we're just assuming from the assumptions of the problem that n is so big that, you can't put multiple rows in there. So we're going to miss every time we do this, is what he's saying, right? So now we want to look at what actually the patterns look like in memory, right, of this inner loop here. So if we touch something in this row and we're walking across that row to do the inner product, pair up these guys with going down the column to create that result, right? As soon as we touch the first guy, we're assuming 4 of them fit into the block and the cache in the assumptions of the problem. So we get the next 3, we get hits, and so we get a miss rate of 25% walking across that row. But touching the B matrix, we're walking down a column, so we're missing every single time we touch that guy, right? And then we're touching this one element in C. And so we'll just assume that we don't even bother with taking that into account. We're not going to add that into our computation, right? Because he's just this one guy, right? But these are varying the K. So these are the ones that are really costing us, right? So this is our loose back of the envelope kind of analysis here. Looks like, we get, 1.25 out of that. So what if we start screwing around with moving the loops around like we did before and see if that has any effect, right? So if we pull the J out to the top and then have the I and the K in the middle, what does that look like? Well, on the inner loop here, still walking across this row, you're holding I fixed and moving the K across. And over here, you're still holding the column fixed and walking down the thing. So that didn't have any effect at all. It's the same exact thing we had before. So what if we turned it in to take the K and put him on the outside, the K-I-J? Well, that's kind of an interesting thing. But we got a slightly different thing that we have to do here. We have to create some temporary variable to hold this a sub I k value, and then just reuse that a sub I k value over and over and over again over here, right? And walk across the row, multiplying all of those things in that row, right? Row K, varying the J, the column, right? By this element that we plucked out there, right? And we're storing them in the C sub ij, where we're varying the j, holding the I fixed. So that's a row-wise access. So since we're doing two row-wise accesses now with this way of doing it, right, we are hitting in the cache a lot more, right? We're just ignoring this because he's one element. And then we got some hits. 1 out of 4 things was a miss, right? So moving that loop out there to the outside actually is having an effect, allowing the cache to help our program run faster. That isn't the way you would think of doing this if you looked at it in the math book, right? And that's really the moral of the story. A programmer doesn't just take some algorithm out of an engineering book or a math book or a chemistry book or something and just parrot it down in code, right? That might be the way that a chemist would code it up, but a programmer, a computer scientist, right, isn't going to just parrot the thing down. You're going to look at how it runs on the computer, right? So the implementation of the algorithm is extremely important. When you study the analysis of algorithms and you take those classes, they're completely going to put blinders on you, and you're only going to look at the order of complexity of the algorithm. And you're just going to ignore any realistic implementation details that are concerned with implementing it on a real computer. And what we're trying to teach you here is, well, that's really not the way you do it, because it makes a huge difference. Maybe 100 times. Your program might run 100 times slower if you just completely concentrate on the algorithm and its order of complexity and pay no attention whatsoever to how you implement that algorithm on the actual real computer. So that's a sort of false mindset that you'll get reinforced in your head taking those analysis of algorithms classes. Of course, we would prefer an n squared algorithm to an n cubed algorithm. Although if n is really small, it doesn't make a whole heck of a lot of difference, frankly, right? But that's the mindset they're going to teach you in those classes is, oh, we always want that n squared algorithm. We don't want that n cubed algorithm. But they're going to completely ignore any real implementation details. But the real implementation details really make a drastic difference into how fast does the thing run on the actual real computer. So this one, now that we permuted them around another time, we're going to move the I out, put the K in the middle. And so we're still grabbing a point here and just blasting it across all of those guys, doing row-wise access. So it behaves just like the KIJ did, right? Those look pretty good. Well, this one's horrible. If we move the J out there and the K here and put the I down at the bottom, we've now got to have this temporary again, but we're doing two columnar accesses in these two terms on the inner loop, right? We're holding the row, the column fixed, the K and the J on the inner loop and varying the row. So that's columnar access, and that really stinks, right? So the question is, well, why can you move these loops around? Yeah, you got to compute the same result. Well, yeah, I've got to end up computing n cubed things ultimately to put in this thing over here on the right, the result. But the order that I produce those n cubed results doesn't matter as long as I get them all, right? So that's the idea, right? So when we look at it, they fall into these three groups. The one that we copied out of the math book, it's 1.25 was our sort of average there. And then permuting them, putting the K on the outside made it 0.5. And then when we did put the J on the outside, that was really horrible. The two columnar accesses, it went up to 2, right? So this would actually run, the one in the middle would run a lot faster than these other two. And it doesn't really matter whether you do KIJ or IKJ, they pretty much the same thing. But that isn't what you would come up with if you just looked in your math book and said, well, how do you multiply matrices, right? So that's what a programmer has to come up with, right? Is knowing that that's going to have an effect on the speed of the program because it's going to more effectively utilize the cache doing the row-wise accesses in these two terms on the inner one. Now, the point is that when you run it, as n gets bigger, it makes a big difference, right? How big is my array, right? As it gets bigger and bigger and bigger, it's going to make a bigger and bigger difference. Doing those columnar accesses is going to eat your lunch, right? These ones up here, right? So we can do these analysis, but the point is the implementation of some algorithm, being a programmer, programming the computer to use the actual characteristics of the real actual computer is what you're trying to do, right? You're not just living up in abstract land, taking some algorithm and just parroting out what the statement of the algorithm is in code, right? So how can we get better than this first blush through? Well, there's a technique you'll need to learn called blocking. And this particular technique is not applicable to all the problems in the world. In order to be applicable, the problem must be such that you can divide it into a bunch of little subproblems, and then solving the subproblems collectively adds up to solving the bigger problem you started out with. Fortunately, matrix multiplication has that property, right? It doesn't make any difference what order we produce the n cubed inner products results, right? As long as we get to all of those terms eventually, right? So if we take the one we started out with, the IJK, copy it right out of the math book, that's our compute this 1 point by doing a row and a column access, right? You get the final product that you want as the result over here, right? And if we look at what that's doing into the cache, right? Assuming the parameters of the assumptions of the problem where we still got, 8 doubles will fit in a cache block, which is pretty realistic in this case because 8 doubles is what? 64 bytes. What's the block size on the real computer? It's 64 bytes, right? So that's realistic. If I could fit 8 doubles in a block, then on the first iteration through there, I'd get n over 8 plus n misses. Why am I getting that? Because the row-wise access, I'm getting hits after the first touch, right? So I get n over 8 for the row-wise access, but the column-wise access, I miss every dang time, right? So that gives me a 9n over 8 misses walking across that row and walking down that column to get the first result in the corner up there, right? So after I finish that pass across that row and across that column, what is left sitting in the cache after I do that? Well, my cache can hold 8 doubles, right? So the cache could be holding these guys that I see here and these guys in red up here, right? The last 8 of them fit in some block. And then maybe there's some other blocks that these guys fit in 8 wide, right? So that data is sitting there. The question is am I going to take advantage of it? The fact that that data is sitting in the cache? Well, not really, right? Because then what am I going to do? I'm going to start back at the beginning of the row and I'm going to walk down the next column, right? So the thing I'm touching here is obliterating what was already in the cache, and the thing I'm touching here is obliterating what was in the cache. I'm not in any way taking advantage of my what was left after the first pass, right? So the second iteration gets me the same mess. It gets me n over 8 plus n misses. And so if I do that for every single pair of rows and columns, I'll get my n squared times that number of misses, which gives me a total number of misses of something on the order of 9/8 times n cubed. There's the n cubed products that we end up with showing up there. So that doesn't look so great, right? So then the idea is, okay, well, what about this? What if rather than saying, okay, just walk across this array and compute up all these results for the big, huge result that you want, what if I just focused in on one little small subsection? Right? Give me these results in this little sub problem here, right? That's this big, not the whole big monster thing I want to finish with, right? How would I get all those results? Well, I'd have to walk across all of the things that are rows in there. So that would be all of those guys. And I'd have to walk down all the appropriate columns that this thing falls into. That would be these guys, right? And I'm looking at what the block size is of my cache, right? If I got a block size of B, then I'd need B times B elements in my cache that I could hold to hold all of that stuff, right? Well, now if I did the code like this, here's my I, J, K, and I'm going to say, now I want to solve this little sub problem here, right? I1, J1, K1, and I'm only going to concentrate on computing up all of those little guys in the result, right? What does that do? Well, that means that when I get back to reusing some stuff for the next pass, the stuff that I want is in the cache from the previous pass. And I'm not obliterating it like I did before, right? Going all the way back to the beginning of the row, uh, so I'm just concentrating on this little sub problem because the data needed for that sub problem actually fits. And I just move the box around and solve all those little sub problems, and I'll solve the original problem. You can only do that, of course, if the nature of the problem lends itself to being decomposed into computing these little subproblems, right? But if you can certainly use this general technique called blocking so that now we take advantage of the locality of those references fitting in our cache. So that's the basic idea of this blocking concept. And if we look at it, we get a lot more hits, right? The first iteration, you're getting the block size squared over 8 misses for each block. So that's not so great. But afterwards, in the cache, I'm getting a lot of hits because the stuff that I'm touched in the first pass was in there. That's what I needed in the second pass, right? So that's the basic idea of blocking, right? So you can combine blocking with other techniques like we looked at before. And so if I did the blocking version of my matrix multiplication, I still got to compute n cube results, right? But my hits and misses were different. The amount of misses I had in the naive solution was 9 over 8. The amount of misses I had in the blocked solution is 1 over 4 times the block size, which would lead me to believe that, oh, well, make the block size bigger and bigger and bigger. But the problem is, once you start making the block size bigger, you eventually make it so big it doesn't fit in the cache anymore, which ruins the whole effect, right? So the largest possible block that we could have would be limited by the cache size, right? In this case, they're saying 3 times the square of the block size, as long as that will fit in your cache, then you could. So this analysis leads to some conclusions that in order to make this specific program run good on this specific computer, I have to exploit the exact characteristics of the cache sizes for that specific processor, which means that if I optimized it for this processor and I drag my program over to some completely different processor with different cache sizes and characteristics, it wouldn't be optimal for that. I'd have to redo the optimization. Well, that's exactly what they do in these libraries of routines that we use on supercomputers to solve all these scientific problems, right? You have libraries like LinPack, linear array package and stuff, right? And they have people that when you come up with a new processor, a new motherboard, has this many processors on it and all this stuff, right? They go in and they start tweaking around on these library codes and they come up with one that is optimized to some degree for that specific processor. Then when you invoke the code out of the library, they actually go in and look at what model CPU it's running on and drag in the code out of the library that's optimized for that specific processor and the problem size that you're trying to solve. They have it both ways. They have it optimized in all sorts of combinations. If you're trying to multiply two arrays that are these dimensions on this processor, this works out best because we tested it and we know it works out best. So they actually do that. And there are legions of people out there whose job is to do that, right? To come up with these library codes that are optimized for specific processors so that when I run my science calculation on a supercomputer that's going to run, gazillions of iterations of something, right? The core of which is some mathematical computation, whatever that computation is, whether it's matrix multiplication or whatever, we call those the kernels of the computation. And so we spend a lot of time identifying what these kernels are. When you do all these different kind of science problems, what is it you're actually computing? What math are you ultimately using? We identify those kernels and then they optimize code for those kernels that is processor specific to get the ultimate speed out of it. And then when you run your thing on the supercomputer, you're pushing it through there as fast as you can, right? It makes a big difference when you're doing some calculation that's going to run on the supercomputer that takes 30 days worth of processor time, right? You'd rather it take 30 days than 130 days, right? And so these tweaking these things makes massive differences. And so they have it optimized down to the specific processor across the specific problem size for all these libraries of math code that are out there. So when you write your code and you're going to do some calculation, use their library. That's the moral of the story. If you're not able to use some highly optimized library that somebody already did, then look at your code for what you're doing that's not a bunch of library off the shelf code, right? And make sure you're doing these types of analysis too. But in order to do it, you're having to do things ultimately that are very processor specific. But since all the Core i7s have pretty much the same cache sizes, with the exception of they'll vary the size of the L3 cache. On some of them, it's bigger than others. And the actual number of cycles for each of those levels is slightly different on the different models too. So, but in any event, that's what you have to do to write code that runs fast on the computer. Any questions about that? So we have a lot of different flavors of optimization now, right? So the basic rules of the game for test are always the test cover everything we to that point. That's what the rule of the game is for the test. So we won't have completed our discussion of chapter 9 by the time we take the second test. So there may be a little smidge of stuff at the beginning of chapter 9 that we can get to before the second test, but we won't have completed it till the end of next week, which means the bulk of the material in chapter 9 will be on the final, not on the second test. But the rule is everything we get to before we take the test is tested for on the test. So tomorrow we begin our discussion of how virtual memory works on the computer. One of the really neatest tricks that we've come up with in computer science to utilize these computers in a very clever way is this trick called virtual memory. And so you need to understand how it works and what we use it for on the computer and how it solves a bunch of problems for us. So to really understand what's going on the computer, that's one of the pieces of the puzzle we have to fill in. How does the virtual memory stuff work? So that's what we'll do next. We'll skip over to chapter 9 and do that chapter, and that'll be the last topic we'll have time to get to this term. So there's a quiz, survey, whatever you want to call it out there about the scheduling of the second test. Go put your vote in, and we'll review that tomorrow and see when everybody wanted to have it. We have your final project due Friday, right? And you have a new homework. I think it's due next Wednesday, if I remember right. That's the final homework for the class. So we're getting down to the short rows now where everything is filling up in the score spreadsheets, filling in all those missing entries. So, any questions about anything? Remember, it's Wednesday, so office hours are at 1, not at 2. And either I see you there or I see you tomorrow. Questions about anything before we go? All right. Well, I'll see you later then. Have a great day. Sun's out. Amazing.